With a bit of background on the program, I'd like to turn things over to Ali Service for a quick overview of the Caledon Green Development Standard. Ali is the climate change specialist at the town of Caledon and has been working on this initiative for the past little while. And so excited to hear from Ali in terms of some of the background and how it's relevant in terms of the context of today's presentation on LID as well. Over to you, Ali.
Thanks, Matt. Thanks for inviting me. Yes, like Matt said, we've been working through Green Development Standard, have a draft kind of just about finalized and planning to bring it to council later this spring. So I just wanted to touch on the components related to green infrastructure and stormwater low impact development techniques that we're focusing on, for new development. So this is primarily for new development, but I think some of the lessons can be used elsewhere as well. So you can go to the next slide. So if anyone's unaware, green development standards are, a policy measure that's increasingly being implemented by municipalities across the GTA and Ontario to establish sustainable and climate-friendly community design features through the planning application process. So this is something that's applied through site plan control. And we're looking at, building-specific measures around energy and emissions, trees, stormwater features, active transportation, all of these things. So certainly for Caledon, green infrastructure is a big part of where we want to go with our green standards, ensuring that new development has adequate green space. Next slide. I guess just to back up, our Green Development Standard has three key theme areas. So one on community design and mobility, the second on green infrastructure, and the third on buildings and energy. So I'll just focus on the green infrastructure theme area today. But really the purpose is recognizing the many co-benefits that come with enhanced green space in urban areas. So improved neighborhood aesthetics, stormwater runoff, improved water quality, addressing urban heat island effect, particularly as neighborhoods become denser, and improving urban habitat for pollinator and other species. So kind of bringing all of those and looking at those benefits holistically. Next slide. I found this a very helpful diagram. I'm sure many of you are familiar with it from Green Infrastructure Ontario Coalition of kind of what we mean by green infrastructure when we're talking about it, especially in the context of, of development. And really it spans the spectrum from natural assets like wetlands, forests, the natural features that are already on the landscape. And the focus really for us is protecting those. And then low impact development techniques, both enhanced assets like rain gardens, green roofs, street trees in urban areas, as well as engineered assets, but would still be considered green infrastructure, like rain barrels, permeable paving. And so just as distinct from kind of traditional gray infrastructure like our bridges and roads. And that's really what our Green Development Standard, in draft form at least, is focusing on, really that full spectrum that's covered under the green infrastructure component. Next slide. So what Caledon is piloting through our Green Development Standard is a green area factor. Kind of struggled just to figure out, how we could, enhance the quantity and quality of green space in urban areas, but allowing for still, flexibility in how developers could meet that, recognizing the different conditions on each site. So this kind of approach originated in Sweden. It's now used in a number of cities in Europe and the US. And we kind of modeled ours after the city of Seattle's green factor, which started in 2007. And for them, it's implemented through their zoning regulations. But really it is about enhancing that green space, but using a flexible framework. And so we are rolling it out as a pilot. It's something that we want to, hasn't been used to a large extent in Canada. So we want to kind of test it out, work with applicants to see how it's operating on the ground and kind of refine it from there. So next slide. So basically what it is a score-based tool that sets a green cover target for different development sites. And that target can be met through a weighted menu of options. So there's different targets for a low-rise residential context, decreasing to an industrial context where we recognize there's, it's a different use, different space options, but we still want to see at least a certain minimum green cover on site. And those targets, again, can be met through a variety of ways, both on the roof and on the ground. Next slide. So Caledon's green area factor is comprised of 4 kind of categories: preserve features, so really wanting to give the highest weighting of points to preserving features like trees, wetlands, grasslands that are not already protected by our existing provincial or town policy. New planting includes trees and landscaping, and obviously we're kind of emphasizing the larger canopy covered trees that provide shade for cooling effects, and we're prioritizing native planting of landscaping. And then there's a category of stormwater solutions, so that can include again on the roof, green roof, blue roof, bioretention, infiltration trenches, permeable paving. There's a number of solutions that we know can have a positive environmental impact and enhance green cover on site. So again, recognizing that it's not just about stormwater, not just about green cover, but they really work together to provide those multiple benefits. And then there's some bonus elements around community gardens, food gardens, enhancing the percentage of native planting, and looking at kind of innovative options like integrating solar with green roofs. And then the next slide. So it's just a snapshot of what it looks like. If anyone's interested, I'm happy to, you're welcome to follow up, and I'm happy to provide this to you. But the sheet on the left is really just the score sheet and shows kind of the weighting of factors along the left side. And really what developers or our consultants would be filling in is the worksheet on the right. So just tallying up the number of landscape areas, the number of planted trees, the number of trees preserved, and then divided by the site area to get your score. So it looks a little bit complicated on the slide, but really it's just a way to add up the amount of green cover on site, and allows us to really have a more objective way of tracking and measuring the amount of green cover on site, and making sure that we're also kind of meeting our targets around tree canopy cover and green space that we know is a big priority for our residents. So that's kind of it in a nutshell. I'm looking forward to hearing from the other speakers to dive down a little bit more in depth into the stormwater features and tools. And yeah, happy to answer any questions later on.
Awesome. Well, thanks for that overview, Ali. I think it's very relevant to what we'll be talking about today, and looking at some of the co-benefits that you've mentioned of LID, as well as tools that can help people with planning, what LID makes the most sense for their landscape. Just a quick question around the pilot itself. Is there a certain timeline that folks should be aware of for this pilot in terms of an end date, or if there are, thinking about applying, when would be the best, and how would be the best way to do so?
Yeah, I mean, we're still taking the Green Standard to Council sometime this spring. So obviously we'll have to go through and be approved, and then, in force and effect sort of later, probably closer to the summer. And that's when we'd start to look at, this would be required as a submission. We will be flexible on the actual achievement of the targets, because we want to take that time and space to make sure that it's, it's working well on the ground. And we are asking, some developers on a voluntary basis to just, take your existing landscape plans, fill out the tool, so we can again start gathering some of that data and refine it from there. But then it'll be in a pilot phase for about a year or so until we have that information.
Awesome. No, well, that's very helpful, and I guess for folks on the call, gives people a bit more time to kind of prepare and think about this and LID for their locations as well. So certainly when things are live and open for applications, we can let people know through our GreenBiz resource hub as well.
Yeah, sounds great.
Awesome. Well, thank you, Ali. And now I'll turn our focus back to today's workshop and our speakers and some of our learning objectives for today as well. Really, we're hoping that when you come out of the other side of this session, you'll have learned about the benefits of low impact development for stormwater management for your site. You also learn how to use a number of tools that have been developed by the TRCA's experts that can create, an action plan for your business. You'll hear from subject matter experts, as well as, different approaches that are kind of local in context, and also have the opportunity to connect with other folks on the call, especially when we get to the discussion section or through the chat as well. It's a great opportunity to connect with people that are also, prioritizing these issues or thinking about these issues and looking for other people to discuss with, share with, and so forth. So without further ado, I'd like to take the opportunity to introduce our wonderful speakers that we have for this session. I'll start with Eustace David, Senior Research Scientist at TRCA. Eustace manages and research and development tools, frameworks, and guidance documents for climate adaptation with the goal of making the state of knowledge more accessible to practitioners and decision makers. He's currently coordinating a number of projects that help assess and communicate impacts of climate change for local municipalities and evaluate adaptation efforts, including nature-based solutions. We also have Daniel Philippi, a research scientist at TRCA as well. Daniel works with the Sustainable Technologies Evaluation Program, also known by the acronym STEP. He has over 10 years experience in the environmental field and has developed several flood and climate change related training programs and courses, educating homeowners, government staff, consultants, ICI or MERB owners on the importance of adopting appropriate low impact development for their sites. And then finally, we'll have Christy Graham, Program Manager, also part of TRCA's STEP team. Christy has spent over 15 years carrying out research and creating tools to support the implementation of stormwater management best practices. Her area of focus are urban runoff and low impact development. So very knowledgeable folks from the TRCA, and we're really excited to have this opportunity to share some of this expertise on a very important topic for many folks, especially with spring right around the corner. It's something that is top of mind for many people as we're looking at, rains ahead and melts, even though I feel like most of the melt might have already happened in many parts of the GTA. So without further ado, I'll turn things over to Daniel for an overview of stormwater management and low impact development.
Thanks very much, Matt. I'll actually just share my screen if you don't mind.
Yeah, no problem.
And hopefully everyone can see that now.
Yeah, looks good.
Perfect. So thanks very much. My name is Daniel Philippi, as Matt mentioned. I'm a research scientist with the STEP group. So I'm just going to provide a quick overview, an introduction to low impact development, or LID as we call it, and then how these types of features benefit stormwater management, apart from our usual kind of end of pipe controls that we've engineered at the municipal level for the last couple of decades. So just a quick overview. STEP is not only just focused on, STEP isn't just focused on stormwater management. We're focused on both energy, so climate mitigation efforts, as well as stormwater management, which focuses both on kind of a co-benefits of mitigation and some climate resilience or adaptation practices. So as a STEP collaborative, it's actually a grouping of Ontario's largest conservation authorities, TRCA being the largest here, of which Caledon is within our watershed. Our neighbors over to the west, which is Credit Valley Conservation, which actually has a small slice of Caledon as well. And then Lake Simcoe Region Conservation Authority to the north. So this collaborative brings together researchers, program managers, planners, engineers, and the like. So we can come together and actually collaborate on a much larger watershed scale to make sure that either our pilot projects, our ongoing monitoring projects that Christy manages on our team, or new tool development with that Eustace manages quite a bit, that we can come together and make sure these projects can be shared outside of our watershed to this larger watershed collaborative. So we focus on low impact developments, as I mentioned before, erosion and sediment control for urban construction developments that include some LID and how to best protect them. Salt management, which is becoming a major issue across not only our jurisdiction, but the wider breadth of Canada, being that chloride is a very intensive chemical that stays in the environment and it's hard to get out. So LIDs can help out with that and choosing the right salt tolerant or halophytic plant species, and then natural features restoration, so green infrastructure. So when we talk about what stormwater management is and what green infrastructure is, we want to kind of start with what is low impact development and how does it fit within this. So low impact development and green infrastructure, these fit together quite well. So green infrastructure is kind of like this large umbrella term. It's a great way, the way I usually present and think about it is the large term of sustainability. Sustainability is this large umbrella term, and a lot of different things can fit under that larger term. Green infrastructure is very much the same. So green infrastructure, it's providing collective societal benefits, but it also providing this multitude of economic, environmental, and social benefits. So intrinsic and instrumental value to our communities and our neighborhoods. So when we talk about green infrastructure, we can talk about, it can be as simple as a natural marsh or wetland area, or it can be a more detailed and engineered feature like this large bioretention / rain garden feature that was set up at a public school out in Brampton, Ontario. So if we then want to take green infrastructure and break it down a little bit further, green infrastructure kind of falls in these two larger categories: low impact developments and then natural vegetated systems. So natural vegetated systems are which appear obviously naturally. So that could be wetlands, that could be woodlots, that could be large fields, grasslands. All these areas are natural vegetated systems, but because they have permeable land cover, they're able to provide that stormwater management benefit just as they are. Whereas low impact development is more of engineering spaces and features that can mimic these natural vegetated systems on a more close kind of lot level or source control benefit. So examples of this, you might have heard of a lot of features known as bioretention features. A lot of people also call these kind of rain garden features. So this is just a little bit more of an engineered feature compared to a rain garden with some underground pipes and conveyance. And then permeable pavements, which I'm sure a lot of you have heard about, and a bunch of different types, which I'll go into a little bit later in today's presentation. So then breaking that down even a little bit further, low impact development can also be broken down to non-structural LIDs and then structural LIDs. So when we talk about low impact development, it's not only just placing a bioretention feature in a specific area on a commercial site, on a public site, or on a residential site, but it's also the thought process as a non-structural LID. It's a planning and development idea. So an idea of non-structural low impact development planning would be minimizing hard surfaces. So we're actually trying to reduce the amount of, as we call it, impermeable ground cover. So this is ground cover that's not going to soak up or take in heavy precipitation events, and it's going to create more runoff, which can lead to flooding issues downhill or downstream. But it can also drum up a lot of water quality issues. So it's pulling out a lot of suspended sediments, oil and grease, brake dust from your cars, or any other kind of industrial processes, and then that's dumping that waste into kind of the end of pipe, which is not going to always be cleaned out. So that's going to be affecting our water quality downstream. The other piece is also preserving natural features. So on the slide we have here, we're kind of showcasing a development kind of idea where you can see this development here of homes. It's actually built around a lot of natural features. So you have these open kind of swaths of agricultural fields and natural kind of grassy fields. And then you've kept a lot of those mature trees. So that's helping with erosion issues. That's helping with high wind issues. But then it's also helping with co-benefits, heating and cooling costs, and benefiting the actual homeowners there. And then there's been studies, numerous ones before, which showing having more mature trees is also benefiting the people who live in those neighborhoods, their mental well-being as well as their physical well-being and health. And it actually increases the value of their home as well and their property. Now, going over to structural LIDs, this is what I'll be talking about most today, is the actual features themselves, the engineered features of permeable pavements, green roofs, bioretention, infiltration chambers and infiltration trenches, stormwater tree trenches, and the like. So now we've kind of talked about what green infrastructure is at a high level, what's low impact development and natural vegetated features at a high level, but now we kind of understand what low impact development is, but why do we need it? So a lot of our areas, a lot of our neighborhoods, a lot of the communities we've lived in over time have gone from the picture on the left, so pre-development scenarios, where we've had this natural kind of vegetated features, large woodlots, fields, and the like. And we've now moved over to this area where we have a post-development area. And as we can see on the slide here on the right, in this post-development scenario where most of us live, we can see there's not too much permeable land cover anymore. Yes, we have kind of this baseball diamond here. We have this park space. We have some large mature trees in this more mature neighborhood, but we can see just the sheer amount of impermeable land covers. That's all the homes, all the roofs, sidewalks, roadways, larger buildings and schools down the bottom left. So the idea with LID is we're trying to allow and make sure we can still build homes, still have development occur, but at a more sustainable level. And we're trying then to mimic our pre-development levels with regards to stormwater management. That's kind of the idea we're going for. So with that said, here's an example of kind of just a very simple line graph showing if you're going to have a major rain event, how is your runoff rate going to be affected? So in a pre-development hydrology, this is how our water cycle would work. If we have natural ground cover, so imagine this is a forested area, you're going to have high levels of evapotranspiration with mature trees and vegetated systems in place. You're going to have minimal runoff, only about 10% because you have so much permeable land cover. And then you're able to refill both shallow and deep infiltration. So when I say refill for deep infiltration, that is renewing our groundwater sources. So if you lived in the country, your groundwater sources, meaning your well systems, is able to take up that fresh water down your aquifers and water table below. And shallow infiltration can make sure that natural vegetated cover can still proliferate and grow going forward. And as we can see, our runoff rate kind of low. It starts low. So imagine the rainstorms happening right at the Y and X axis on the far left of this graph. You have a small little hump. That means the amount of runoff, it's only about 10%. And then it falls back down fairly slowly. So you're not having issues of pooling or potential flooding events. Now, if we move forward and we've increased our impervious cover from 10% to 30 to 50%, meaning we're in kind of an urban setting, maybe even a town setting, like a Caledon area, we can see our runoff rate is increasingly higher. We have post-development that's showing that runoff rate really peak high. Our peak discharge is increasing that much more. It's much faster. And that's where you're going to have issues with lot level flooding and major flood events. So we can see we've tripled our runoff. We've decreased our evapotranspiration just a little bit to have the water go back up into the atmosphere, but we've really decreased our deep infiltration and shallow infiltration. And with this, we can see formerly we would use stormwater management ponds. We still do. And these are kind of end of pipe controls, but it's not always going to control an increase in runoff volume. And it's also going to cause some pollution in our end of pipe receiving water bodies, which likely here is going to be Lake Ontario. So what are the consequences of higher runoff? Well, flooding could be one. The example pictures we have here, the one on the left, I'm sure a lot of you remember, this happened in Toronto. We have the GO train there, July 8th of 2013. We had more rainfall this day than when Hurricane Hazel hit back in the mid 50s. We can actually see a little rescue dinghy in the kind of top left of that picture, pulling people off the train because those are the emergency lights. All the electrical systems were shut off. And the Don Valley Parkway is unfortunately in a flood fringe. It's in a flood spill zone or a floodplain. So that means, as we're going in those arterial roads into the city, they're in a large floodplain area. So that needs to be better protected. But this is the issues we fall into. So this amount of 2013, the infrastructure damage was 850 million estimated. That's only what's covered by insurance. So if you have people living in basement apartments, which potentially aren't certified through the city or aren't legal, A lot of those people lost a lot of their assets, a lot of their things, and those weren't covered. So that amount of 850 million is significantly higher than what's posted. The other example here, we have Finch Avenue, torn out in 2005. That cost 671 million in insurable losses. It increased a lot more, closer to $1 billion, and this was back in 2005 dollars. So we had the culvert started creating a sinkhole. There was too much leakage, and it completely wiped out. Finch Ave here, and we can see just the sheer amount of water coming through after a major rain event as well. So that's another consequence as we have higher runoff, more urbanization and development. The other example is we're going to be impacting our water quality and how's that going to affect our thermal kind of effects within our water systems. So we can see here, City of Toronto, we can see a lot of suspended sediments, all that kind of muddy water that's coming out from our river systems because of likely high construction activities further upstream. And that's just depositing it out in our receiving water body of Lake Ontario. Thermal impacts, if we can adopt levels of green infrastructure, the example here with FLIR imaging, we can see the kind of fuzzy dark purple images on the right. That's an example of a green roof in downtown Toronto. It's at 74 degrees Fahrenheit. We can show in the FLIR imaging the roof right next to it on a commercial building with no coverage. That's showing it's 151 degrees Fahrenheit. So just talking about heating and cooling costs is another benefit, is the kind of co-benefits or economic benefits of having green infrastructure. And then stress to aquatic life. The example, the picture on the top left, high levels of suspended sediments. That's going to likely kill off and affect our endangered species. This example here is a minnow species called red-side dace. These will be wiped out because they really need clear water for hunting and then nice rocky bottoms for spawning. So we're seeing a lot of these, which we call bioindicator species. If they leave a certain reach or certain area of our stream systems, we know there's heavy construction or disturbances either within that reach or further upstream. So this brings us to, we've always had this idea of an extended detention approach. So if we're having flooding, if we're having stormwater management controls, what is the best way to manage these? So over the last couple of decades, we've been focusing on high levels of rainfall when it comes down. In pre-development, if you remember those kind of quick histograms I showed you or graphs I showed you, you have our pre-development, that's our kind of peak discharge. We see our post-development with no stormwater management controls. And then within this period, especially kind of the 60s going forward to the 90s, we started post-development. So we had stormwater management ponds to kind of control this high level of peak discharge and potential for flooding. So we can see in this area here, it really drops that peak discharge level of having stormwater management ponds or dry ponds to control those levels and help with some level of water quality. But there's this large area beneath. That's our runoff volume difference. So we can see the difference between post-development, which we've had since the 90s, or even before that, and up to the 90s, and then pre-development. There's still that area, that hash mark in between. And this is where we at STEP and at TRCA really think that we can help out with helping with the discharge level of increasing. Design assumptions aren't always going to be realistic. You're still going to have flow regimes affected within your streams. We're trying to mitigate loss of natural flow pathways. There's going to be cumulative effects of watershed development that aren't always going to be managed. The way we want to address this area between that hasn't been managed before, we really think this is an opportunity for both green stormwater infrastructure and low impact developments. So we're rethinking. We're trying to go from large centralized, picture at the top left, 2 large stormwater management ponds, and then the small distributed. So a bunch of smaller LID features throughout neighborhoods. The benefit to developers is we can always say, with less stormwater management ponds taking up, developable land, you can increase that amount of land and actually increase the amount of development there. Moving from single function over to multi-function. So having permeable pavements, soak up water in a rain event, it's also going to water your street trees nearby. We're moving from pipe, sewers, curbs, and gutters, which constantly have to be updated, and it costs billions of dollars in infrastructure assets updates, to soils, vegetation, and hardscapes, which can be a little bit easier and more costly to manage, or less costly to manage. And we're managing flow rates within our stormwater management ponds, and we're trying to then manage the water cycle at a large scale. So here's a number of benefits. I know I'm getting close on time, and I want to kind of touch on a bunch of our features that that then Christy and Eustace will be talking about today that you can use within our LID step tools. So what are some types and functionality, and how could they benefit larger commercial properties? So there's a number of different types of LID features. You know, we've talked about bioretention, we've talked about permeable pavements, trenches, chambers, large rainwater cisterns or rain barrels, green roofs, stormwater tree trenches and tree boxes, and the like. So I'm just going to touch on just a few of these today that actually resulted in a major kind of research project we conducted back in 2012 out to about 2014, 2015 with Honda's head campus or head office here just off the 404. So the first example we have is bioretention. This is kind of the poster child of LID when it comes with TRCA, talking about low impact developments. So really, when we look at it, a lot of people will call these kind of rain garden features, and really it's an engineered kind of rain garden. So what will happen is you'll have your mulch layer, you'll have your filter media, which is this specialized soil media which can uptake water quality, can benefit water quality, can uptake high levels of phosphorus that you would get from fertilizer being spread further upstream, high levels of nitrogen and the like. So it's a mix of sand and some added additives which can be put in, iron fillings and the like, which can take up those higher levels of contaminants, and also help and maintain growth of your natural features. And then we'll have this clearstone level below, 3/4 inch clearstone, which can act as a water storage layer. So it can hold water underground in this feature for long periods of time. If there's too much water being held in the feature, especially during a major rain event, we have something called an underdrain or a perforated pipe, and that will actually bring water off-site and will connect that into the local municipal system or the stormwater system. So it can actually go into the storm sewer and be brought off-site, but it's actually cleaning the water coming into this feature first. Here's an example of a bioretention cell we have out on Mississauga Road. I think I might have to click it here, and that should work. So we can see for the example of this bioretention cell, we actually had river rock laid on the bottom of this feature. So this allows for the movement of water to go throughout, because you'll see when we change the camera around in just a quick second, we're seeing this is quite a heavy rain event. You can see this feature goes all the way down to the stoplights at the very end here. And so we have these check dams in between. This allows the water first to pool a little bit, allows it to go through that filter media I talked about below. It can capture in the clearstone gravel layer, hold it there for a little bit longer, and then an underdrain pipe can actually bring it off-site when there's too much rainwater. But these check dams allow for infiltration while still allowing, when there's too much water, to go over top or in between these larger river stone rocks and go throughout the whole feature. So we're not just infiltrating right at the front where the water's coming in from the inlet from the road. So other examples, dry and enhanced swales. You'll see these a lot. Swale systems can be more engineered, where you'll have kind of a better kind of underdrain feature in there, or there will be some level of filter media. Another example of this, or they're known as bioswales. So they both help with conveyance, bringing water off-site, but they can still help with increasing infiltration on-site in these kind of ditch-style systems. And you can make them actually quite beautiful with having more levels of river stone, so add some mulch layers, and you can have some other types of plants be planted in them that are salt tolerant, and then drought and water tolerant as well. So they can handle those dry or wet seasons. The other example we have, permeable pavements. There's a bunch of different types. We can have porous concrete, porous asphalt, and then you can have the pavers themselves. So the way we break them down is most of the time the pavers themselves are impermeable, but the joint material in between those paver stones are permeable, and allows water to go in between them. So you have the bedding course, open graded base reservoir. You have another underdrain which can bring water off site, and then you have this open graded sub base reservoir. So this allows a lot of cleaning of that water coming in. It also helps in winter maintenance when there's those kind of warming seasons. It allows water to go through this system and doesn't allow as much pooling or ice forming in your parking lots. There's also rainwater harvesting. The most normal or most the most kind of average example we would see as homeowners Rain barrels is an example of rainwater harvesting. You can use it again on your flower beds in your gardens. But then on a more commercial high-level scale, you can have large rainwater harvesting cistern tanks. So this example here, and try and remember this image, this large cistern was actually installed at Honda's head campus and still used there today. You can see the sheer size of this. You have a tamper, which you would have a person move that along. You have this large ladder up on the side of it. You have the monitoring well here to check the water levels, but then you have this large backhoe digger here at the back. You can just see the sheer scale of this. So this cistern alone could hold almost 64,000 liters of water. The reason this was used on Honda campus's head office, they wanted to use this both to retain stormwater off their major production rooftop, hold the water there on site, and then they were actually able to have this be used for their watering system. So they're able to actually water their larger fields out there. And they noticed during the study when we were working with them, the water reuse for their irrigation system, they actually saved $16,000 over that summer study period. So just over 4 months' time. The other benefit to it, and I'll just show in the next slide, this is the commercial parking lot at Honda's head campus. So when we worked with Honda, we came in and were doing the monitoring for the site. They wanted to focus on stormwater management, so they wanted to improve water quality. They wanted to have better water conservation and reuse, and they wanted to minimize the reliance on end-of-pipe controls or stormwater management or the minor system that you would have at the municipality. They also wanted to achieve LEED certification and meet Honda's wider international sustainability vision and goals, as well as having a nice minimalist aesthetic on site. So this was done and completed back in late kind of 2000s, and then we started doing the LID adoption and implementation and monitoring system back in 2012. So the different features we have on site, I've kind of touched on all of them. We have vegetated swales along the left side of the property. That's along 404. We have biofilters, which are a mix of kind of infiltration trenches and bioretention cells. We had permeable pavers along their parking lot here, 1,000 kind of cart or stall parking lot here. We have biofilters up here as well. And then this is the large production and distribution center for Honda Canada. This whole rooftop, it collected the water. This was running the cistern here. So you can see on the aerial image, this is how large the underground cistern was, collected water underground here. And the benefit of having this cistern and a small overflow dry pond, Honda decided we don't want a stormwater management pond. We want this large underground cistern and an overflow pond. This allowed for the development of a large baseball diamond, basketball court, and large kind of regulation size soccer field for all their staff to use. So that was a benefit for them on site, is to have an area for their staff to use. And we can see an example of how everything looked at the end. So we had natural drainage from their bus stop location, so employees could come to and from work. We had really nice paving and vegetation set up in the courtyard. These are the permeable paving stalls. So permeable paving wasn't used over the whole parking lot. It was used in specially kind of designed area stalls where water would drain to it in a heavy rain event at the end of each of the major kind of parking lot stall areas. You had large amounts of vegetative practices used. This was the large rainwater cistern I was just talking about. The running or fitness path, they had a large kind of enhanced swale here along the side. They had filter inlets and their biofilters installed throughout, and they were able to actually save a lot on their site. So in terms of the amount of land cover that LIDs took up, it was only about 2%. The concern with using a traditional stormwater management pond and end-of-pipe controls, that was going to take up more than 6% of the area, and that's what they were able to change into available kind of play areas for basketball court, to baseball diamond, the soccer field. And we are actually monitoring the results of this and found that it was actually cheaper for them to do these LID features instead of having a stormwater management pond. And the local municipality there was going to require them to have their own stormwater management kind of internal miner system on site. So by having these LIDs implemented, it was a lot cheaper for them going forward, and they were able to move forward with a much more beautiful site. So thank you very much. That's it for my time. If you need to reach out, ask about any of our research projects, or any of kind of the current work we're doing right now, there's my contact details, my phone and email. And thank you very much for your time.
Awesome. Thank you so much for that, Daniel. Thank you for that overview and for, really kind of getting into some of the co-benefits of LID. I think that's really important context for our next two presentations in terms of the many options of LID that are available for different sites and different kind of considerations and how they might integrate together as well is certainly something that I'm sure is top of mind for folks. For anyone that does have questions for Daniel, please do feel free to enter them into the chat or save them for our Q&A. We'll have a discussion with all of our presenters after we get through our next two presentations. But at this point, we can turn things over to Eustace for an overview of one of our tools.
Hi, everyone. Matt, can you give me a thumbs up if you can see my
Yep.
screen and hear me?
All good. Can hear you and can see your screen. Looks great.
That's awesome. Okay, just give me 1 second here. Great. That was great, Daniel. Thanks for that overview. I think that really sets us up nicely for this presentation. And today I'd like to present on designing and costing your LID sites with the software called the LID Treatment Train Tool version 2.0. My name is Eustace David, Senior Research Scientist, as Matt mentioned. I work for the Ecosystem and Climate Science team, and you may have heard from one of my colleagues, Sharon Lamb. We work on climate science, climate adaptation. We do climate research and integrate that into many projects at TRCA and with our partners. And one of the things that we do is also see how climate and land use affects hydrology, both at the watershed scale as well at the site scale. And so the treatment train tool, the tool that I'm going to be presenting on, helps us assess that impact of climate and land use change at the site scale. So let's dive right into it. First, I'd like to provide or introduce the treatment train tool and provide overview of features and limitations, present the use case, when and why would you use the treatment train tool, and then leave you all with a very short case study. So first off, low impact development. We just heard about that from Daniel. Essentially managing stormwater runoff as close to the source as possible in a way that mimics the natural hydrological processes of that area. And essentially, this is what the software that we're about to talk about does. It helps you evaluate how that site functions before it was developed and after it was developed with impervious surfaces, and how we can then bring that site back to mimic its natural hydrological processes by including the structural and non-structural LIDs. So the LID treatment train tool was actually developed by a collaboration between Toronto and Region Conservation Authority, Credit Valley Conservation, Lake Simcoe Region Conservation Authority, as well as Golder Associates, now part of WSP, the consultants that we retain to do the actual coding and development of the tool. And we were also supported by Ontario Ministry of Environment, Conservation and Parks. The purpose of the tool is really to analyze the effectiveness of low impact development site designs. So this could be the decisions you're making regarding the type of land covers that you are having. Perhaps you wish to reduce your impervious cover or maintain a certain pervious percentage of your land of your site. So to be able to evaluate those non-structural LID designs, as well as those structural LIDs that Daniel mentioned, including bioretentions, rainwater gardens, green swales, enhanced swales, but also those larger end of pipe practices, including stormwater ponds, wetlands, and even underground storages, as the example that Daniel just shared with us about Honda campus. And the way it's able to do this is the tool is able to calculate the amount of runoff that would occur as a result of every single stormwater event. So for a particular rainfall volume, how much of that rainfall volume actually translates to a volume of runoff, and then routes that runoff off of those different land covers that you have from your site to your practices, your structural LIDs. And it can do that for a single LID, but it could also do that for multiple LIDs in series that provides a treatment train. So this is why it's called the LID treatment train tool, because we're really encouraging people to have that treatment train to improve and this amount of stormwater quantity and quality you can get from your site. And so once it goes to the LIDs, it could potentially go to an end of pipe treatment, and then you see the impact all that had on your stormwater control. Once it does that, it does produce a number of robust results that helps you evaluate the performance of those LIDs and the structures you put in place. Namely, it can look at the rainfall volume reduction. So what percentage of the rainfall volume on your site falling and reaching your site actually leaves your site? And you can set targets for that and see if you're meeting your targets. We talked briefly about the peak flow, the runoff rate that will leave your site. This has implications for the downstream erosion that could occur as a result of all that flow leaving your site at once. And you saw a very a large impact it had on big roads like Finch. But for site level, you can still have impacts to downstream rivers. And so how can the LIDs you're putting in place have an impact on that peak flow leaving your site? We could also look at the pollutants leaving first generated on your site as a result of your various land covers. And particularly, we're focused on total suspended solids that carry with it a lot of other pollutants, but also specifically total phosphorus. And this was developed specifically for Lake Simcoe region. They're concerned about the amount of phosphorus entering Lake Simcoe, but also it is part of stormwater criteria in a lot of other jurisdictions as well. So we can calculate the amount of phosphorus and total suspended solids being generated from your land covers, but also then the amount that's going to be captured by the various LID structures that you've put in place. And that's only possible because we are also calculating a preliminary water balance. So rainfall coming in, what proportion of that infiltrates? What proportion of that is going to filtrate through your LIDs? How much is going to evapotranspire? And as a result, what is the remaining amount that's leaving your site? The LID treatment train tool, we also focused on providing a very user-friendly design so that it's able to be used by others outside of stormwater engineers, right? So we have a lot of stormwater models, they're quite technical, and you really have a large learning curve, but we wanted to focus on providing a user experience that a new user who doesn't have stormwater modeling experience but has something to contribute in terms of site design, whether you're a planner, you're a property manager, you're the landowner. It allows you to communicate your perspectives and your opinions through this user-friendly visual interface. So for version 2, we added 2 new features, one being trees available as an LID option. So we decided to go with this because we saw that a lot of municipalities and our partners, their go-to green infrastructure or LID was first to plant trees on their site. And that's excellent for a lot of benefits. And we really wanted to also be able to have them be able to measure the impact of trees on the stormwater quantity and quality control as well. And hopefully down the road, we'll be able to provide more of the co-benefits that trees are providing as well. But for now, it's just the stormwater benefits. It provides some guidance to practitioners about what type of trees to implement and how many trees to implement to get a certain impact on their stormwater control. And we've basically brought in the research from iTree suite of tools that you may have heard of out of the US. That is the go-to software for analyzing anything of trees. And so we brought in all that information into the treatment train tool. The treatment train tool now is the only tool that considers trees at this scale, in this detail, while also providing all the details on other structural LIDs. So it's unique in that sense. And the trees that we decided to include are those that are available in the GTA quite prominently, but you could change the values to represent any type of trees that you wish to include. And finally, the last update that we made to the treatment train tool is to also include a costing module so that it could provide a very high level estimate of your capital cost and your 25-year maintenance cost for your LIDs. So you can do that for every single LIDs you put in to your site design, and you could also get a nice cumulative value for your entire site. This is possible by bringing in all the research that and details that are in the STEPS LID lifecycle costing tool that Christy will present on. So that's a very detailed, robust tool, and we use that tool to essentially model standard design for every single LIDs that we have in the LID treatment train tool, and then to come up with a relationship between the size of the practice and the price, how that price changes with the size of the practice. And we are getting very good estimates. So this is a good, it will give you a good ballpark number at the conceptual stage, and then you will then graduate to the LID lifecycle costing tool that Christy will present on once you're closer to pulling the trigger on putting these LIDs on your site. We do have some limitations, and these are as a result of making sure that the tool is simple enough for a lot of our users. So we don't have time series analysis, groundwater routines, or calibration modules. And really, we didn't see the benefit of that for a site level tool. However, we did implement an export function from the treatment train tool to the SWIM 5 model. And that's a robust model that engineers use internationally and accepted internationally. And so you could potentially start designing in your treatment train tool, get a bunch of perspective from a number of stakeholders. And once you're happy with that, pass that on to your stormwater engineer, who is going to then export it and continue their detailed design in SWIM 5, where they have all these other advanced features. So the use case. When would you use the LID treatment train tool? So this image is sourced from TRCA SWIM Criteria 2012 and really outlines a workflow of what you would undertake when you are implementing SWIM practices on your site. So first, you need to obviously understand your site conditions, your constraints, and your sub-watershed. And then you would need to define a design criteria, our target that you're trying to meet. And sometimes it is just for aesthetics and for other co-benefits. But when it comes to stormwater, you can set a stormwater quantity and quality control target. And sometimes if you are trying to bring back your site to mimic that natural hydrological balance that it once had, you can set a volume retention threshold, like 25 millimeters. I want to capture the first 25 millimeter event or volume of every single rainfall event. And that's, we've calculated that around for GTA, 25 to 27 millimeter threshold, if you're able to capture and retain that on your site, that's actually mimicking a natural hydrological cycle there, because natural areas are able to capture and retain 90% of the rainfall events. And if you're capturing 25 to 27, you're capturing 90% of the rainfall that's falling on your site. So once you set your target, then you could start screening for stormwater management practices. Which LID practices would you want on your site based on how it looks? What's your constraints? Do you need underground? Do you have a lot of space above ground? So that really helps you make those decisions. And then once you pick, then you need to assess your effectiveness and see if it meets the criteria that you've set out. And if it doesn't, you have to go back and do this iterative process to make sure you're meeting it. Sometimes you are meeting criteria, but you've over-engineered it. And so this is where our second, our functional upgrade of having the cost is really beneficial. You can see if you're meeting the criteria or if you're really surpassing a criteria, but it's costing you a lot more. from that high level estimate, then you would go back and actually make sure you're not over designing it and saving on your budget. And once you're happy, then you could do that export function, send it to Swim5, send it to a stormwater engineer, and they'll have everything that you've already put in the treatment train tool, and they can continue where you've left off. So why use the LID treatment train tool? It really has efficient workflows. As you can see on the screen, as soon as you start drawing and clicking and finishing a certain step, it tells you what the next step is. So for example, here you're drawing a subcatchment, and it all of a sudden slides out and lets you know what parameters you need to fill out, which makes it fairly quick for you to set up a model and run. It also highlights anything that you're missing or any errors that are there. And as a result of it being visual, it allows you to collaborate. We ran this workshop very recently for sustainability practitioners, and we had them in groups of 5. Not all of them were modeling, but all of them were able to provide perspectives and opinions based on the site they saw. So you could actually Google your site, bring up the Google imagery, and start designing right on top of your site. This makes sure you don't over-engineer or under-engineer things, and allows you to have that collaborative conversation. It also has minimal startup requirements. So one of my pet peeves is having climate data in the actual format required by the model to run the model. But here, we've already put that in. We've already have a number of data sets that you can pick and select based on your area, how you want to represent your site with the climate. And you're able to run that. And for relative comparison between pre and post development or pre and post retrofit, those data sets are going to be quite sufficient for you to get up and start running that tool. And of course, it provides those robust results that I've already mentioned, and we'll see how good those results are in analyzing the efficiency and the effectiveness of the LIDs in the case study that I'll be presenting soon. So here quickly is another case study that we like to present. This is an actual subdivision that is put in place. It exists today in Newmarket. It has a number of LIDs, and they did that in lieu of putting a stormwater pond. And today, normally we'd pick a site that doesn't have LIDs, and we'll say conceptually, let's put an LID and see how it would do. But because we have this site, we have detailed plans for the site, we have monitored results for these LIDs, I thought we'll take it backwards. So we'll go from the detailed design and see how we would have conceptualized it in the LID treatment train tool, and then compare the results that are coming out of the treatment train tool to the actual monitored results for that LID on that site. So while it has a number of LIDs here, I like to show and look at the exfiltration trenches. So if you're a stormwater engineer, these things look like what you look at every day, but sometimes for others, it could look quite complex. But essentially, this is, if you can look at it as a profile view, water is coming into a catch basin, into this manhole, and these green rectangles here are the exfiltration trenches. And whenever you do stormwater modeling, it's essentially, you have to keep in mind that water runs from uphill to downhill, and there are certain bottlenecks that control how fast the water can flow. And if it doesn't flow into one direction, where does it go otherwise? And so here, the first bottleneck that we encounter is this exfiltration into the native soil. So how fast can the native soil accept that water? And if that rate is slower than the rate of water coming in, the water is going to build up a little bit and flow to the next treatment train, the next exfiltration trench, and it will have another opportunity to infiltrate water into the native soil. If not, it will build up and leave the site. So how you design these exfiltration trenches will depend on your target. If you'd like to make sure you don't have runoff from the first 25 millimeter of a rainfall event, you want to make sure that there's no buildup of water past the second exfiltration trench for a 25 millimeter event. So that helps you reassess and the effectiveness of the LID. So how do we put something like this? How would we have conceptualized this detailed design in the treatment train tool? Well, quite simply, this is the actual site that we pulled up. This is a vector map, but you also have the choice of using a satellite imagery. And we first have to draw the drainage area. What part of the site is going to drain to that LID? And then the LID is represented here in green. Now, we know this because of the detailed design, but if it's a new site, you'll need to know how water is flowing, or if you have the opportunity to change the grading, then it's really up to you how much water, how much area is going to drain to your LID. Now, there are guidelines of how much impervious cover can drain to a certain percentage of pervious cover, and you should follow those guidelines that are also implemented in the treatment train tool. But once you set that up, I'm basically having water from that blue outline fall into the green outline, which will then flow into a pipe and to an outfall. And at this outfall, I can measure the change in water level depth, which basically will change as water level is increasing or decreasing in the exfiltration trench based on the amount of infiltration or overflow. So now we could actually compare that water level depth to what we measured on that site in that manhole. So let's see how it does. So here we have a graph. On the y-axis, we have the water level depth in that manhole that I mentioned. On the x-axis, you have timeline. We actually modeled it long-term from July 2018 to December 2018 based on when we had the data. And on the top, we have rainfall events. And the longer the line, the more intense that rainfall was. The blue is the observed water level depth, and the orange is the modeled water level depth from our conceptual design. There's no calibration. We didn't go back and forth. This is basically pulling out the conceptual design from their stormwater criteria and stormwater report, excuse me, and putting it in there and running it with the rainfall events that occurred during that time period in that location. So you can see it's a pretty good match in terms of intensities and how it performs. There are some instances where it deviates, especially in those green highlighted areas. One, the winter time, our monitoring equipment doesn't do great after it falls below zero, so there could be issues there. But the model is also not that great for winter modeling. But when we focus on summer, it does a great job. And also, there are some instances where it deviates because there could be a rainfall event that occurred at that site, but we didn't capture in our rainfall gauge, or vice versa. But otherwise, I think at a conceptual stage is doing a great job in terms of assessing the performance. And so this gives us confidence when we look at seeing if it's meeting our target. So if you recall, I mentioned that 25 millimeter target. So we could run a single event and see if we put in a rainfall event of 25 millimeters, how much of that actually is retained on site. And here, based on our results, 92% of that rainfall event is captured on that site for that drainage area going into that exfiltration trenches. So if 25 was really your target, you can go back and resize your exfiltration trenches to make sure it meets it. But you get to test out different climate scenarios. So this is where we could include or increase resiliency to our site. So right now, 25 millimeter might be the threshold, but if you're thinking 30, 40 years from now, and you want to be resilient to the changes in climate, perhaps you want to bump that up to 30 millimeters and make sure there's enough redundancy on your site to capture those rainfall volumes in the future as well. So Ray Thaler, who was one of the original engineers for this site, he did his master's on developing this site in the model. And from his master's thesis, we pulled out the actual tender cost for these exfiltration trenches, which ended up being roughly $300,000. And if you can see, our costing module actually estimated $273,000. And this is without mucking around and making any changes, just using, before we even saw this result. So this is very similar to the other results that we've seen in the past with other studies. Our costing module is providing a 10 to 20% difference in those results, which is a great ballpark figure to start off with at the conceptual stage when you're trying to make decisions and balancing cost and budget with meeting your stormwater criteria target. So finally, the treatment train tool is useful to communicate site design opportunities and concepts with reasonable estimates for stormwater performance and cost. You can use your conceptual design as a starting point for detailed design to pass on to your stormwater engineer. And here is the site that you could download the tool, sustainabletechnologies.ca/LIDTTT. And there's also a help desk that if you need some assistance, we can help you with that for a single model, or you could invite us to do a workshop or some type of training to get you up to speed on this tool. So let us know, and thank you for your time.
Awesome. Well, thank you for that, Eustace. Thank you for that overview of such a helpful tool. And I think for many on the call, people will be coming with different sites or property sizes, but I think a tool like this can really help ensure that there is that detailed planning no matter how large the site. We did have one question that came through the chat that I think we could just ask quickly around if green roofs can be included in the model for the TTT. I'm just curious if that's also a consideration as an LID.
Yes, definitely. We don't have pricing on the green roof because there is such a large variety. It's hard to standardize such a design, but that's certainly possible. We don't have a separate module for green roofs, but you can use other LIDs to mimic a green roof.
Awesome. Well, thank you for that. And just for the sake of time, we'll move things on to Christy, but just encourage people to please continue thinking about questions for our presenters, or even, if you have done LID on your site or have questions about what you're considering implementing this year, it's a great opportunity to ask as well. So Christy, we'll turn it over to you.
Sounds good. Hi, everybody. Okay, is it sharing screen okay?
Sharing
Matt?
screen, I'm getting a little bit of an echo.
Okay.
Sure.
Give me a second, I'll grab my headset.
Sounds good.
How's that? Is that better?
Perfect. Thanks, Christy.
Perfect. Okay, no problem. Hi, everybody. Thank you for having me here today, Matt. Just going to close this. Okay, so everybody, as Matt said, my name is Christy. I am a program manager for the STEP group at TRCA. I'll be telling you about our LID lifecycle costing tool. It's been a really successful tool for us over the years, and I'm always excited to share it with people because it was one of the first Excel-based tools that I helped develop with STEP. I'm just going to give a quick overview of the history of the tool. It all started back in 2013. TRCA developed the lifecycle costing tool to help industry professionals easily calculate the initial costs and lifecycle practices of site-specific LID designs. It started, we were working with a grad student named Mariko Uda, and she created conceptual designs for each of our LIDs based on the existing design guidance that we had at the time, with a consistent drainage area associated with all of them so that we could see how they all priced out differently. The conceptual designs were primarily costed using an RS means database. It's a database of thousands of construction costs comprised of material, labor, equipment, and also quotes from local companies for anything that wasn't included within RS means. The tool does include an inflation estimate, and believe it or not, it was actually still accurate with the COVID cost inflation, but we have recently done a new update as well. Throughout the years, we've had a number of updates. The first release happened, and then the second update happened in 2018, where we did our first cost update. We're trying to do them every 5 years. We also adjusted some calculations and minor bugs that were found at the time. In 2021, we released another version. This time it's just changed the interface to try and make it a little bit more user-friendly. And we also added the addition of costing curves, which I'll speak about later in this presentation. And we are currently working on the latest version, version 3.1. I did hope to have it available to share today, but we are still working on some of the back-end coding for that. I hope to release it in the next week or two, and we'll let you know when that is available. The existing tool is available on the STEP website. If you wanted to look at it, you can just go on STEP website and search Lifecycle Costing Tool and you'll find it. But as I said, we're going to have a new tool out with new prices and a little bit of a change in the interface as well to hopefully make things easier for people. So the tool currently has 10 LIDs, which include many vegetative practices, such as bioretention, enhanced grass swales, vegetated filter strips, green roofs, and dry ponds, as well as some underground hardscape practices, such as infiltration chambers and trenches, permeable interlocking concrete pavement, pervious asphalt, which can also be used to cost out conventional asphalt. And then as well, rainwater harvesting. And lastly, one conventional swim practice was added a few years ago, and that is wet ponds. And so that's to be able to better compare conventional practice against the LIDs. The tool has 5 sections for each of these practices, but there's only 2 that generally require your input, and that will be the design and construction estimates section and the operation and maintenance section. Those will have the green user input cells. Those will be particular to your site details. And then there will be purple cells that are editable defaults. So the defaults are based on our research, anything mentioned in our planning and design guide, which you can find on the STEP website or on our wiki. And you can change those because you might not do everything as we would suggest it, and that's okay. So there are things you can change. As well, if you have made changes or if the tool doesn't size it within a certain range for your site, you will get a design error flashing just to let you know that something has gone wrong. There are also a number of other tabs that we did open up in one of the previous releases. They used to be hidden tabs. It's all of our background calculations, so you can see where the costs are coming from if you are so inclined. There is a lot of information there. I don't think most users go there, but we are trying to be more transparent with the tool, so it is available for you if you would want to look at it. Okay, so how the tool works, we have the main tabs, which are called the LID and swim tabs, assumption and sizing tabs, which are grayed out, and then costing tabs, which are also grayed out. And these just sort of work with each other. They pull cells from each other. They take data from each other. All of the user inputs that I talked about before would be on the LID and swim tabs, but there are also editable fields under the unit cost tabs. So if you have a particular cost for something that's different than what we're using, you can use that cost, such as how much your maintenance costs, how much you pay somebody to clean the maintenance, or things like that, as well as assumption are also user editable. So if you have a different way that you clean something, or a different way you size something, you can change those details. Mostly, I think you will be ignoring the costing and assumption tabs, so that the information is all there if you need it. And these tabs all do work together for the information that you do input for the site to create a simple summary on the LID and swim tabs. And if you're interested to check these out, you can check them out. Okay, so let's take a quick look at some of the sections within the tool. So this is an example of one of our LID tabs. It's the enhanced grass swale. So each one starts with a quick overview at the top with buttons showing the different sections. So if you just want to hop down to cost summary, if you want to go over to the back-end calculations or table of contents, you can just click these buttons and move there quickly. All the information provided here is design guidance that it comes from our planning to design guide, either on our STEP website or the wiki, and as well as our operation and maintenance suggestions. Below that is where you can start doing your input. So this is step 2 for design and construction estimates. And as you can see, there are not many fields that you need to enter here. On the left is really the only fields you have to enter, and those will be your site details. It'll be things like drainage area, how it's going to connect to a storm sewer, anything related to if it's a different size practice, like how you want the length and width to react to each other, and also generally native infiltration. And I know that for much of Caledon, there are tight soils. And so there was some concern a few years ago about how they would be able to handle infiltrating practices. But we did do an evaluation over 10 years ago now that showed that when sized correctly, an underground trench system could easily infiltrate the 25mm target that Eustace had mentioned during his presentation and match the pre-development water balance in the area. So infiltration practices are very possible and workable within the Caledon region. You'll also sometimes be asked for different variations. For permeable pavements, for example, you'll be asked whether or not it's going to be a full, partial, or no infiltration design. And as well for rainwater harvesting, you'll be asked about what type of cistern it is, plastic above ground, below ground, or concrete below ground. All the information that you are asked for should be readily available from the designer of the practice. The cost will be automatically updated on the right-hand side once you've input the data. All of these green user fields here are just cost adjustment to say yes or no whether or not you want the cost included. So if there's something here that you don't need included, you can just switch it off no so that it's out. So if you already have curbs and in place, you can just remove it easily. As I said, all the costs basically come from RS means. And there are some that are local vendors where we ask them to quote specific things such as the cistern tanks or catch basin cleaning. Now, so when we were doing our first major update to the tool, we started to ask ourselves, how well is the tool actually doing? And by this point, CVC had a lot of detailed costs from some recent projects that they did. So they decided to do sort of a somewhat blind test, where one staff knew the actual costs for the project and the other went through the tool to see how the tool did relative to the actual costs. So on the left is the average of the bids that they received for this Glendale rain garden. And the middle column is how the tool did with the defaults without being changed. As you can see, it was a little high, it was 30% high, but then the user on the tool went in again and adjusted the defaults to match the scenario to match the reality, I mean. So why did the cost go down in this case? So the design in this case did not include a gravel storage area. There was no pea gravel. They used amended soils instead of filter media. All of these are things that the tool would have had as defaults. So once those were adjusted, the tool estimated a cost within 3% of the bids that were received. They did another analysis that I'll show you. So this was the county court biofilter swales. We actually monitored this a few years ago. And so once again, when they went in with just the basic site information, it was about 30% off. This time in the other way, it was a little low. And the reality for this site was that the bioswale was constructed much larger for the drainage area than the tool would have assumed. And this was because it was a high visibility pilot project. The city really wanted to see it do well, so they sized it quite large compared to the drainage area. So once that was adjusted and taken into account, the tool again was within 5%. So the sites, there were other sites that were included in this sensitivity analysis. I won't go through them all, but from these, we do believe that our costs are pretty accurate. The third section within the tool is the maintenance and lifecycle costs, and you'll see there's no specific user inputs here. There's just a lot of defaults that you can adjust. And this is because our recommendations are our recommendations. They are pretty detailed and they are for very visible sites, and they're basically best case scenario for what you could do. But as we all know, that's not often what happens in reality. So you are able to just change things here. You can change how often something's happening, so how many years go between doing it. The occurrence, whether or not it's periodic, just happens one time, or is going to never happen. You can just choose ignore. And then you can choose how many times it happens every year. So if your site is pretty clean and you have catch basins, you can maybe decrease the frequency of cleaning those. And then once everything's included here, the life cycle costs will update. A quick note about life cycle costing. This is kind of a little bit of complicated math. If you don't really know much about economics, it was sort of hard to wrap my head around at the time. It has to do with the value of money now compared to the value of money in the future. And so the tool looks into the future and will determine the costs that you will incur over time. So we looked into this present value costing methodology, and that's what the tool includes. So it's a conventional economic method, which not only adds an inflation amount, but also includes a discount factor. And this is because the value of money in the future is different than the value of money right now. So you can change both the inflation and discount rates, as the use of different discount rates are pretty common between public and private sector areas. For example, a business owner would be looking at capital expenses versus someone at the public sector. They just value things a little bit differently. So why would you consider life cycle costs? It may seem like a lot of unnecessary complicated math, but why it's important is that the cost of the life cycle of the practice over time could help you determine which one you're going to choose. The construction cost will be the current cost, but the cost for operation and maintenance over the 25 or 50-year lifespan will be greatly dependent on the inflation and discount factors that you include. All right, the final section is our most recent addition, and it's the costing curves. And so these costing curves are really a set of equations that you can use to easily estimate the cost of your design if you want to change your design. So let's say you have found your design, but something about your site has changed. You've got half the space that you used to. You can't just simply divide your cost by half, because there are certain things that don't reduce that way within the tool, such as delivery costs, things like that. And so the costing curves will look at the total cost over the full lifespan and give you an equation that you can use to just easily input one factor, generally the surface area of the practice, and then you can size it to see what the different sizes would actually end up costing you. This can be helpful in the early stages of planning your budget if something comes up. So as I said, the costs are not linear, and this is just an example so you can see what I mean by that. So if you're looking at a 100 square meter practice, it costs $13,000. A 50 square meter practice still costs $10,000. So that's only a reduction in $3,000. If you go up to 200 from 100 square meters, you're up to 19,000. So that's a $6,000 increase. So it's not linear. There's things like delivery or overhead or even design that's not going to change based on the size of the practice. And so we looked at a whole bunch of different practices and created different scenarios and focused in on one parameter that was influencing the cost the most. If there was a second parameter that significantly affected the cost, then we did create additional curves for this. So an example of this, I want to go through sample calculation with a bioretention with an underdrain. So these are the default curves that we used. In this case, the main factor that affects the cost of a bioretention is the surface area, but a secondary cost that was quite large was an underdrain. So we looked at what we created two additional equations to go for bioretention, one with underdrains and ones without underdrains. So this example on how to use the costing curve is what is the cost of a typical bioretention that is 500 meters square with an underdrain. So you're going to use the first equation here because it's with underdrain. The A is where your 500 is going to go. So you're going to input that into it, and you're going to get a cost of $339 per square meter of practice. Now, to figure out how much it's going to cost for the whole practice, you're then going to take that 339 and times by 500 to get a total of approximately 170,000. So it's a pretty easy way. So if you wanted to do 200, you just input the 200 in those two bolded places, and then you'll figure out the costs. Hopefully that makes sense. It is generally pretty easy to do. It's just sometimes people forget this second step to get the total cost. Eustace did mention in his presentation that the treatment train tool does include the costing curve information as well, so that you can cost it out. So the neat thing is that you can have your specific design costing curve for your site, and then you can input it directly into the LID treatment train tool in these two sections. And so it's really neat, so you can just have it really specific to your site. So some final tips for using the tool. You want to have your site details as close as possible to reality. You don't want to ignore the defaults as they may not match your design that you're planning on. You should adjust as much as you can and remove items that you don't need to include if it's already on site. You can adjust the drainage areas to cost out different practices, or you can use the costing curves for your design. And last, please ensure that you enable macros in your file. The costing curves particularly need macros to be enabled, and there's also just some general functionality with the tool that needs macros to be enabled. Last thing, as I'll just mention again, is that we are hoping to release version 3.1 in the next coming weeks, and we can let you guys know when that goes out, and the website will be changed to announce that it is a new version that's been released. So that is it for me for now. I don't know how we're doing for time, Matt. If we have time, I could open up the tool and show how that works.
Yeah, sure. Yeah, we have a few more minutes, Christy. That'd be great.
Okay. So I'll close that. Hopefully I'm still sharing and you're seeing the tool. Okay, so this is the life cycle.
It's still the slides right now. Might need to move the tool over.
Okay, I'm just going to stop sharing. Share and screen. Okay, is it the tool now?
Yeah. Yep.
Okay, whoops. I want this to go big. Sorry, trying to move this. Okay, well, I'll just show it like this. So this is the introduction page that just gives you quick little details. There is a table of contents, so you can click on a button and get directed to a site. I'll make it bigger like that. So here's the enhanced grass swale that I showed. I'll just scroll down to the drainage. This is the site design information. So I'll just input basic site design. So 2,000 square meter practice. I'll put in a catch basin, no driveway, swale shape. I'll just make it linear this time. I'll say it's going to be a 1% slope, check dams, nope. No NA, and project, I'm just going to say no. And so once I finish inputting these green cells, you'll notice all the costs opened up here on the right. And so you could go in and say cost adjustment. If you put it to 0, then I think the price won't go over or something. If you can increase it if you don't agree with the price, you can adjust it that way. We see that everything is okay. We don't have anything red there. We'll go down to the maintenance section. So you can change anything you need to here, and it will automatically adjust the cost over there. And the summary will be on the right-hand side. So you can see we've got an inflation of 3%. And it gives you the average annual maintenance that it will cost you every year. And then scrolling down a little bit further, there's just a handy pie chart that just shows you how much the cost breaks down over the different things. In this case, generally materials and installation is generally the biggest cost. And then there is the costing curves. And so this is a button you can just click and it will create your own costing curve for you. So there are your 2 equations. If you changed your design and you want to try it again, you just clear the regression using the gray button and you can click the blue button to do it again. I'll go through one more example really quick. So for permeable pavement, you just put in the drainage area, and if there's an impermeable portion draining to the drainage area, you can add that. Native soil infiltration rate, design type, I'll make it partial, drainage period, and total length of the permeable pavement, I'll just say it's 100. Once again, everything started costing for us. The colored cells here are just the highest costs associated with it. Again, everything updated here for the maintenance. And yeah, so you can do that. I'll take a quick look. I think I still have maybe 1 minute to show you. These are all the grayed out tabs that I mentioned you probably don't want to go into, but if you did want to go into them, you could see how everything is costed. The assumptions tab is where there's user editable. You can see again, it's green. So if you disagree with something here, such as the cost of water. You can change how much the water is going to cost you, as well as unit costs. This is a detailed list of everything and the reference for where we got it from, RS means in most cases, and you can go over to the right and enter your own cost data, and then the tool will use your own cost. Other than that, the rest of these are just sizing things that we have to help. They were just a little bit too complicated to put on some of the other tabs, so they have their own. You generally won't have to look at these, but the information is there if you are interested to see how we cost everything out. And so that is our tool. So I think I'm just going to wrap up there. Thank you
Awesome.
for having me today.